Hi everyone, welcome to another LIC class. In the previous class, we went through the introductions of ICs, integrated circuits, a little bit of a history of integrated circuits, and some applications. Today we're gonna dive into op amps in particular, and a little bit of introduction of op amps, different functions and applications of op amps, and the internal structure of an op amp or operational amplifier. So what is an operational amplifier? Operational amplifiers were initially made using vacuum tubes. They were pretty large. They were not made in the form of integrated circuits. They just put a bunch of vacuum tubes and later on transistors together to build an operational amplifier. These operational amplifiers have unique features. One main feature of these operational amplifiers is their high gain. So they provide pretty good gain, voltage gain in particular, and they could be easily designed to build different filters as well. Nowadays, we built them in IC packages. We don't put individual transistors together to build an op amp. And we have good control on their characteristics. When you build an IC, you can mass produce them, so you can have thousands of ICs that have the same features and the same characteristics. They are universal gain blocks. Usually we buy them in IC packages, and then we add a couple of resistors to get the desired gain. And we can add capacitors, resistors, inductors to build low pass filters, high pass filters, band pass filters, and so on. And I'll explain more about that. Initially, they were made for analog, but you can use both DC and AC signals in the input of an op amp. Most op amps have the main terminals are in op amps. We have 5 main terminals in op amps. Some op amps may have more, like a DC offset and so on. Some might have just 5. But the 5 main terminals that we have in an op amp are the positive VE power supply. And this VE power supply is a DC power supply, usually from positive 9 to positive sometimes 30 volts. But the most that I have seen in, for example, the LM741, which is the most popular, is positive 15 volts DC. And negative VE is a negative DC power supply, which is usually negative 15 volts DC. So between negative 15 and positive 15 volts DC, we have 30 volts DC. So the DC power supply is just to turn on the op amp. It powers the power supply for the op amp. It's not giving it any data. It's not an input. It's not an output. It's just to keep the op amp running. Okay. It's a DC supply that you had in a transistor. It's the same thing. Then we have the inverting and the non-inverting input. These are the inputs that we could give the input signal to. We can give it DC or AC signal for the input. So we can, for example, give it a sinusoid or a triangle, or a DC signal for the input. So AC or DC signals, or even a square signal. And then we have one output. If we give the signal to the non-inverting input, the output would be in the same phase. So for example, if I have a sinusoid signal like this in the input, the output would be the same phase, maybe a different amplitude, but it's going to be the same phase, meaning that if in this part, if in this cycle, if the sinusoid is positive and negative, it's going to be the same positive and negative. But if I give the input to the inverting input, the output would be 180 degrees out of phase, meaning if this is positive, here it will be negative. If it's negative, it's going to be positive. So you're going to flip the signal. So the inverting input inverts the signal. The non-inverting input keeps the signal in the same phase. The most popular op amp that we're going to use in this course is going to be the LM741, or the newer generation, which is called the UA741. And if UA741 on top of these has other pins and terminals as well, but all the op amps have these 5 pins in common. Usually they have a positive supply, negative supply. The positive negative supply must be fixed at 15 volts or 9 volts. Usually the operational range is mentioned in their data sheet. And the input is the signal that we give to the system, like a audio signal or AC, a DC signal. And the output is obviously what we get from the op amp. Op amps are usually made in 3 different packages. We have the metal can, or the TO package. We have the dual inline package, or DIP, and we have the flat package. So this is an example of a dual inline package. This is for example, LM741. We have the inverting input that you saw in the previous slide, the non-inverting input, the negative power supply, the positive power supply. And by the way, the positive VE and negative VE are the DC power supplies. And we have one output. And 2 other popular inputs are what we call the null, offset null. And offset null is basically to cancel out the offset voltage, and I would explain that in a later slide. But the op amp usually looks like this. You can have surface mounted or go through op amps. But for 741, pin number 2 and 3 are the inputs, the inverting and non-inverting input, and pin number 6 is the output. The way that we determine the pin numbers, it usually has a notch or a dot on the left side, and then you count from the left side. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So if you have an IC that looks like this, and these are the pins, for example, we don't have 6 pins, but this is just an example. Usually you start, so when you look at from the top, this is going to be pin number 1, 2, 3, 4, 5, 6. Some ICs don't have this part, this gap. They have a dot on one side, and that dot determines pin number 1. So pin number 1, 2, 3, 4, 5, 6. I'll explain more about this in the lab. So the most popular package is this package, but you will also see this type of package as well. But again, 99% of the packages that I've seen it's like the dual inline. Yeah, but the package again, this one has the input, inverting input, non-inverting input, the output, and the offset. No. So what is inside an op amp? Op amp is technically is made out of up to 20 transistors. For a 741. It's sometimes it's from 10 transistors up to 100, but for 741, it's usually around 20 transistors. When we combine these transistors in different configurations, we build different type of amplifiers. So, for example, the one that is in this blue box, this is the inverting amplifier. And we call it the difference amplifier sometimes as well. So if we look at the 741 op amp, we see that we have an inverting input, the non-inverting input, and the output. So the inverting input and the non-inverting inputs are connected, these two sides, pin number 3 and pin number 2. And then at the next stage, the output of here is connected to the next stage, which is what we call a Darlington and a Ziegler pair. So a Darlington pair in electronics, if you have had electronics too, is an amplifier that multiplies the gain of each stage of amplifier. So it's a boosting amplifier, I could say. And through some amplifiers, it goes to the output. So we have multiple stages of amplifiers. That's the reason we have huge amount of gain in an operational amplifier. One thing that we have in this amplifier, which I want to point out, is this capacitor, these coupling capacitors. The coupling capacitors determine the cutoff frequency of an op amp. And the way that a capacitor works is that if you have a huge capacitor, and I make this terminology, if we have a DC signal, it's not going to pass a capacitor. Let me put it this way. So if I have a capacitor and I have a DC signal is not going to pass. The capacitor is going to fully charge it, and then the capacitor would become an open circuit. But if you have an AC signal, the AC signal is going to pass the capacitor. This is an easy way to remember AC and DC and a capacitor. But if you have a low frequency AC and you have a large capacitor, it's like gonna act almost like a DC, and it's gonna be blocked by the capacitor. Therefore, a coupling capacitor, which is a large capacitor, sometimes if you have a low frequency, it's gonna cut off and shut down your amplifier. So these amplifiers usually have a limitation, which is called the cutoff frequencies, and I'll explain more about that. But the cutoff frequencies are determined by the transistors itself, because the transistor has metal terminals. Those metal terminals act like a capacitor. If you put two metal plates and an insulator between them, it's going to act like a capacitor. And if you have extremely high frequencies, these capacitors would just become short circuit, and all of these transistors would become short circuits, and this op amp would no longer work. So transistors have what we call a band, the frequency response, and if the frequency goes too high, the transistor technically becomes like a short circuit, because now you have a capacitor between these two terminals or the pins of the transistors, and a high frequency, these would technically, the current would just jump through the terminals, and you won't have any transistor at all. So these op amps, when you have more transistors, you're limiting your frequency response. These op amps have limitations on their frequency response, and I'll explain in later slides how we can overcome them and answer that. But this slide is in general to show you a normal op amp is made out of 20 transistors, for example, sometimes up to 100 transistors, so on. And these transistors are made into different blocks. We have the Darlington amplifier, we have the difference and differential amplifier, and so on. And we also have coupling capacitors that limits their frequency response. We have three basic operations for an amplifier. We have inverting, non-inverting, and differential amplifier. We have different other operations for amplifiers as well, like transducers, active filters, oscillators, integrator, differentiator, and so on. But the main and the basic operations of op amps are inverting amplifiers, non-inverting amplifiers, and differential amplifiers. So the first parameter, now we're going to speak about different parameters of amplifiers. The first parameter that we have in an amplifier is its open loop voltage gain. Just for a reminder, do you remember what is a voltage gain?
It's the ratio that you get out of what you put in.
Perfect, great. So, and we usually show it with AV. It's the ratio of the output voltage to the input voltage. And we usually show it in dB or decibel. And decibel is actually 20 log of V out over V in. So the open loop voltage gain, and by open loop meaning that we don't have any feedback or anything. So for example, if I ground one of these inputs, and this is going to be my inverting and non-inverting input, and this is my output, this would be Vn, and this would be V out, and the gain would be the ratio of V out over Vn. And we don't have any feedbacks in this system, meaning it's a one-way system. For an op amp, because we have multiple stages of amplifiers inside the op amp, as we saw in the previous slide, this ratio is exceptionally high. It's usually in the range of 100,000, a million. And in an ideal op amp, the gain, open loop gain, I'm going to call it a open loop, is infinite for an ideal op amp. But in real world, it's like multiple thousand. But obviously, this range, this open loop gain ranges from a couple thousand to a million in different op amps. So some op amps, we have 10 transistors, 4 stages of amplifier, the gain would be 1,000. And another op amp, you would have 50 transistors, 10 different stages of gain or amplification, and the range would be up to 1 million for the gain. So, and that's a pretty big number. Usually we don't like very high gains because it makes the system unstable. So if I give it a gain of 100,000, means if I give it 1 volt input, in theory, the output should be 100,000 volts or 100 kilovolts, which is impossible for an op amp to handle. So very high voltage output and gain makes the system unstable. one reason it's not feasible to have a 100,000 volts in the output, for example. And another reason, if that 1 volt has a noise of 0.1, when you put it through this amplifier, it's going to amplify both the signal and the noise. So you're going to have high output of the signal and also the high output. You're multiplying the noise by 100,000 as well. You're amplifying the noise as well. So it's not desirable. And we rarely use an open loop for an op amp because, again, we have undesirable output. The output is too high and it makes our system unstable. Other problem, and I'll show you this later on, is that when you have extremely high gains, you would have very limited frequency response and what we call the gain bandwidth product. And therefore, you are limited to very small frequencies in the output. You cannot amplify a wide frequency in the system. Okay. That's the reason we use a closed loop voltage gain. A closed loop system usually looks like this. You have the main amplifier, and then we have a feedback coming from the output and feedback to the input. So we may have negative or positive feedback, and I'll explain more about that if it's connected to the inverting or a non-inverting input. The gain of the feedback, if it's beta and the main gain is A, the gain would be A would be equal to A over 1 plus A beta. This would be the gain of the closed loop. I'm gonna call it ACL, and A is the gain of the open loop. So you are reducing the overall gain, but you're making the system more predictable, manageable, and controllable, I could say. So in this closed loop setting, if I put like a voltage divider or anything in the place of the beta, I can easily control it with a potentiometer. And I'll explain and I'll show you how we can control the output gain. But in an open loop system, we had no control over the output. For a closed loop, you can easily control it with a potentiometer. So the total gain would be, again, for a closed loop, would be V output again to V input. And again, this is the V output of the system, and this is the V input. Let me see. In an op amp, output signal amplitude is much larger than an input signal. It's usually in the range of 1 to several thousand, and we can easily control that. We usually use negative feedback to be able to control the input voltage by subtracting the output voltage from the input voltage. And I'll explain more about that again later on. I would solve some problems and show you some examples of negative feedback. But the main purpose of the feedback is to be able to manage the output and control the output of and make the op amp control. Other parameters of the op amp, we have the input resistance. Do you remember Ohm's law? What is Ohm's R equal to according to Ohm's law? Perfect. It's voltage over amperage. And we calculate the input resistance in the same way. Our input would be our input voltage relative to the input current. So if I have an op amp which looks like this, I'm going to connect this one to the ground, positive, negative. This would be I input and this would be V input. So V input over I input gives us the input resistance. And an ideal op amp, this input current is usually very low, close to zero. Therefore, the input resistance is extremely high. For an ideal op amp, we want this input resistance to be close to infinite so that the input current is close to zero. So this is for an ideal op amp. Usually the input resistance is from several mega ohms to over giga and tera ohms. So pretty high resistance. So mega ohms for a common bipolar system, and for CMOS or FET, it's in a range of thousands of mega ohms or giga ohms. So very, very high, almost infinite, you could say. A practical closed loop voltage gain ranges from 1 to several thousand, but not that high of a open loop system. And again, when we have a closed loop system, we can control the gain, we can control the input resistance, and we can manage the bandwidth frequency as the frequency bandwidth as well. Then we have the output resistance. It's again the ratio of the output voltage to the output current. So the way that we measure the output resistance is we measure the output voltage when the system is open circuit, or the open circuit voltage, and we measure the closed or short circuit current. So I short circuit and V open circuit, and the output would be V open circuit and I out short circuit. Oh, we have it over here. I didn't even have to. So the output resistance of an op amp is usually pretty low, in the range of few ohms to a few hundred ohms. In amplifiers in general, we like to always have high input resistance and low output resistance. The reason that we love to have high input resistance is because we want to have minimum input current. And the reason that we want to have low output resistance is we want to have minimum loss. As we know, loss is related to the resistance. The higher output resistance that you have, you're going to have more loss in the system. So imagine that we have processed the signal through our op amp, and then after the op amp, the output resistance is 10 mega ohms. So all of that signal will be lost due to its output resistance, and we don't like that. Okay, so we want to have the minimum output resistance, ideally close to zero. Again, because if we have an infinite output resistance, all the signal that we spend so much energy and time to process would be completely lost and eliminated by the output resistance. So we like to have a very low output resistance. On top of that, that adds a little noise to the system as well. Okay. Other parameters, we have the input offset voltage. So for an ideal op amp, the way that an ideal op amp works is an ideal op amp, the gain A for open loop is actually gain multiplied the difference between the positive input or the inverting input. Let's put it this way, V positive minus V negative. So an op amp amplifies the difference between the input voltages. In an ideal op amp, V positive is equal to V negative when we have no inputs together, put into the system. So if we add no input to the system, we just supply it with power. We connect it to positive 10 and negative 10, for example, and we give 0 volts. We should have 0 volts in the output as well, because we're not giving it any input. But during to imperfection and when we are building these 20 transistors, none of these 2 transistors would be exactly the same. When you build them, in the process of building them, they would have a slight difference between them. Maybe they're made out of one single block, but still they would have a little bit of different characteristics. Therefore, we would have a little bit of offset in the voltage, meaning in a practical op amp, not an ideal op amp, if we give it 0 input to the voltage, 0 voltage to the input, we are not going to have 0 voltage in the output, because the op amp, again, is not perfect. It's not ideal. We have several millivolts at the output. Why? Because during the imperfection, the difference between these two would not be 0, and it will be usually a few millivolts. And that few millivolts will be multiplied by this gain, and you're going to have an output in the system. Does it make sense? So, ideal op amp, when we give it no input, the output should be 0. We're not giving it any input. But we don't have an ideal op amps in real world. In the real world, when we give it 0 input, we still get an output, which that is called the offset voltage. We call it the input offset voltage. So an ideal operational amplifier would provide 0 output voltage when 0 volt difference is applied to its inputs. In practice, due to imperfect internal balance, there may be some small voltage present at the output. The voltage must be applied differently to the operational amplifier input in order to make the output voltage exactly 0, is known as the input offset voltage. So, for example, if we give 0 volts to the input and the output shows us, let's say, negative 2 millivolts, it means the inverting input is greater than the non-inverting input. V negative is greater than V positive. How can we fix this? By giving a little bit of offset voltage to the positive. Yes. So we can offset that effect. So we can give a little bit of bias, for example, 0.02 millivolts to the positive, and then V negative would be equal to V positive. Okay. So we can connect an external circuit to the system or external power supply to the system and offset that voltage and balance it. It's like you have these, have you seen those 2-arm scales? And sometimes they're not balanced, so you put a small weight on one of them to balance that. This is exactly the same that we do. So some op amps, like the 741, they have dedicated pins and terminals for the offset, and you add these together with a potentiometer, and you tune the system so you would have 0 volts on the output. So before giving any signals to the input, you would balance and actually offset that voltage to have a 0 volt in the output. So this is one way. Is to apply some voltage to the input offset node. In some systems, we don't have that. What we have, we can give a relatively large negative feedback to the system. And that could, to some extent, fix the problem, or the other way to do it is to use the offset null pins. Typical values of input offset voltage range from 1 millivolts to 15 millivolts. This is for 741. When we use AC rather than DC coupling, the offset voltage is not normally a problem and can be ignored. This is a offset voltage adjustment circuit. We would simply connect the offset null pins, which are pins number 1 and 5, to a potentiometer, and we can connect it to one of the power supplies. And by adjusting that potentiometer, we can cancel that offset voltage. And in this particular example, you can put a 10 kilo ohm larger the resistor, it's going to be better between pins number 1 and 5, and by varying that, you can reduce the output voltage to 0 volts. So as we see here, we have connected both the inputs to the ground, meaning it's 0 volts. So we will connect both to this ground, 0 volts, 0 volts, and V out should be 0. In this case, because V positive is equal to V negative. And by adjusting that offset null pin, we can make it 0. For a 741, offset voltage adjustment range is between positive and negative 15 millivolts. So the other parameter that we have is called the input bias current and offset current. So as I mentioned, in an ideal op amp, the input resistor is infinite, and the input current should be close to 0. So an ideal op amp, there should be no current flowing through the op amp, but in real world, we have some currents flowing into the positive and the negative inputs, which are called the input bias positive and the input bias negative current. The input bias current IB is the average of the current entering the input terminals of a balanced amplifier, or in other words, it's going to be the average of the negative and the positive, or the inverting and the non-inverting. For a 741, the maximum is 700 nanoamps. It's a pretty small number. And for a precision 741 system, a more advanced one, it's 7 nanoamps, positive, negative, which is a pretty small number. The input offset current IOS is the difference between IB minus or negative and IB positive. Or IOS, the input offset is the difference between them, average difference. The offset current is not a big deal. Offset voltage is more usually problematic. So we don't usually care about, because the current is so low that we don't even care about that. Yes, please.
You have a higher input current. Does that create more noise, or does it just cause heat?
That's a great question. So depends on the frequency. Okay. High current usually creates a lot of heat, and heat converts to a lot of noise, thermal noise that we have in resistors. But the thing is, this current is usually so small that heat and noise are completely neglected. The voltage is what creates the noise, and what we call the signal to noise ratio, or SNR. Another thing that you have to keep in mind is that, let me give you an example. The outlet that you have on these walls, what is the voltage on them? Okay, what is the current?
15, 30 amp.
Yes, depending on the breaker. What is the current coming out right now? Nothing. Yes. Why? Because we have infinite resistor. It's air. Depending what you connect to this, you can get different currents, but the voltage is always going to be fixed, almost fixed. You have a little bit of drop. So if I connect the charger to this, the current coming out is going to be 0.1 milliamp. If I connect the dryer to this, it's going to be 10 amps or 20 amps, or AC HVAC system is going to be 30 amps, for example. So the current always depends on the load. The higher the resistances, you're going to have lower currents. The lower the resistance, you have a higher current. So depending on what you connect, always the voltage is going to be 120, but you're going to have different levels of current. Okay, it's like a river that is passing by. You may have a big bucket, you can take more. You may have a small cup and you're going to take less. Okay, the same here. Since all the op amps have a very high input resistance, the current is very, very usually small. And that usually small resistance, usually small current, I'm sorry, creates little, to no noise. The problem is generated by the high amount of voltage that we have and the frequency. It's directly related to the frequency as well. I hope this answers your question. Yes. So again, that's the reason we want to control the current. High input resistance controls a lot of factors and makes job much easier for us. Do you have any questions up to now? That was a great question. Any questions? No? Okay. The other parameter we have the supply current. So the supply current is the current that is coming from the supply. Let me go back a little bit. Or a DC supply. And this current is called the supply current. I'm going to call it DC supply. So it's the current drawn by the op amp from the power supply. Some of them have a short circuit protection built in, some don't. So when we go to the lab, I will show you, we have to be a little careful with the op amps. Sometimes we have to build a circuit protection. The short circuit current is short circuit is 25 milliamps, meaning the maximum current that we could put through the system is 25 milliamps. We usually give it a DC, so frequency, we have the sinusoidal input voltage remaining is constant. Power consumption, PC, is the amount of quiescent power that must be consumed by the op amp in order to operate properly. So we have a minimum power consumption for the op amp as well. The common mode rejection ratio, as I mentioned, op amp amplifies the difference between the inverting and the non-inverting inputs. So if I connect the inverting and the non-inverting together, then V positive is going to be equal to V negative. Therefore, AV, which is the gain times V positive minus V negative, and when these two are equal, this would be 0. Therefore, gain would be 0. But since the op amp is not ideal, the practical op amp is not ideal, you're going to have a small difference between V positive and V negative. Therefore, you're going to have a little bit of gain. And the ratio of the gain, ideal gain to that, is called a common mode rejection ratio. So one important measure of the goodness of an op amp or an op amp circuit is the common mode rejection ratio. Ideally, an ideal op amp are expected to amplify the difference between V1 and V2 with nearly infinite gain due to transistor not ideally some small amount of amplification occurs due to the common signal of both inputs. And a typical common mode rejection ratio is 100 to 80 to 100 dB at low frequency. So supply voltage rejection ratio. In an ideal op amp, when we change the supply voltage from, let's say, 9 to 15 volts, the output shouldn't change at all. But in real world, when you change the supply voltage, the output changes as well. And that is called the power supply rejection ratio. Let me give you an example. Imagine that we have this op amp, and this op amp, well, let me give you a real world example. When I walk into class, you hear a click noise. You hear the click noise? You know what that click noise is? And you see the light going yellow, green and red. You know what that click noise is?
It's a relay contact.
Yes, it's a relay contactor. It's a timer, actually. That has a motion detector. And that motion detector is connected to a relay or timer. And each time I pass in front of it, it resets that time. The reason it does that, because if it doesn't sense any motion or any person, we have different motion detectors as well. This is like a infrared one. Most of them are. The more accurate ones are infrared. So it usually detects heat from the body. So it won't mistake like a car is moving or a human is moving or a cat is moving. So anyway, we have different motion detectors. And the way that it works, and the reason that it needs a timer, because if it doesn't sense any motion for 2-3 minutes, it will automatically turn off the lights. Okay. That's the reason when I pass in front of it, it makes that click noise. Okay. It means it's resetting the timer. But like the timer is like 5 minutes or so, and then it's resetting it. So it's never letting it go down to 0 to turn off the lights. So why did I mention this? All of these motion sensors usually have an op amp in them, and that op amp amplifies the signal that we get, that it gets from its motion sensor, because that motion sensor generates a very small voltage. So imagine that I'm gonna show it here. Imagine that you have this motion sensor, and this motion sensor gets the signal. Imagine that this is like a receiver, generates a very small signal, and then in the output you have a big signal generated. Okay. For this particular system, this is connected to the outlet power, so it won't have any problem with this power supply. The power supply is usually connected to a AC to DC rectifier, and then you have a DC voltage in the supply. But imagine that you have a motion sensor which turns on and off a light outside of your home, and that light is powered by a solar and a battery. I don't know if most of you have seen or have those outdoor lights, which are powered by a battery or solar, and they're motion detected. So they're like alarm or something. They work at an alarm, or in front of your parking or in your backyard or something. And when you walk towards it, it senses motion and turns on the light so you can see at night. Or if you drive and your driveway, it turns on the light or something like that. Those are usually used, and we have a lot of applications for this as well. Those are usually supplied by a battery. For example, a 12 volt battery. And during time, the voltage of that 12 volt battery, we have lab after this, yes? Yes, so I'm gonna continue for like 10-15 minutes, and then because we don't have lab in the first few weeks, and I want to finish this part. So what happens is after a while, the voltage drops. The voltage, because the battery is depleting, it goes down to 10 volts. Now the output signal, instead of being this large, it's going to be half this size. So instead of having 10 volts peak to peak, or 8 volts peak to peak, you have 5 volts peak to peak. And that cannot turn on the light. So that's not good at all. Okay. So we have to design a system in which when the supply voltage drops from 12 to 10 volts, we will still have a constant output in the system. That's the reason supply voltage rejection ratio is very important. We don't want the output voltage to drop when the power supply voltage drops. It will eventually drop at us after a certain point, but we don't want it, for example, to drop when the supply voltage drops from 30 to 25 volts. We don't want the output of the power supply of the op amp to drop from 10 to like 5. We don't, if that drops by 10%, we expect the output of the op amp to drop by 1 or 2%. If it's more than that, it's going to create problems. And this creates a lot of problems in very precise sensors, and I'll explain more about that in measurement instrumentation. So if the supply of an op amp changes, its output should not, but it typically does. If a change of X volts in the supply produces an output voltage change of Y volts, then the PSRR, or the power supply reject ratio, on that supply is X to Y. The dimensionless ratio is generally called the power supply rejection ratio, and power supply rejection if it is expressed in dB. I think it's enough for today. We're going to have a small quiz. And yep, thank you so much. Let me pull up